This is the Math Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hi, I'm Lee Bortons, and it's Monday, February 27th, 2023. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss a math concept each week from our soon-to-be-released math curriculum for families with students in classical conversations communities. Andrew Pudewa talks about how working through the dress-ups and an I&W assignment for writing provides endorphins because it's satisfying to complete a task and then you end up liking writing. Well, I love how math allows opportunities for similar efforts. You know, it takes less time and energy to construct a proof or complete an argument in math than to write a paper or cook a batch of cookies. I'm just happy to have so many opportunities to be joyful. Kirsty, why do you like mathematics?
Well, tonight with the tutors, we were talking about how we get to use our imagination in math, and that idea of thinking beyond what's right in front of us, and that as we use our imagination, it can bring us joy because we're getting glimpses of God's handiwork. So tonight, that's probably my reason, one of my reasons why I love math.
Yeah, expands our imagination. All right, so this is week 8, which means we have 7 more book clubs before we take our summer break. This book club is scheduled or is designed so that parents who want to prepare to teach their children ahead of time. So we're working this winter on next fall's work, and then during next fall's broadcast, we'll work on the spring's work. So to access the Math Map, you need to be a member of Classical Conversations CC Connected Community. Please feel free to participate in the discussion, even if you're not in CC, as we will share the things you need to know on the screen as we talk about math. So each week we consider a part of what we call the exordium for the Math Map. And tonight we're in Math Map lesson 8, equations, which is the last lesson in one-dimension arithmetic. Kirsty, what's tonight's exordium?
So tonight we chose to look at our quote, "Mathematics is the art of explanation" by Paul Lockhart.
So for the rest of you, while Kirsty and I talk about it a little bit, our question for you around the reflection is, what does math explain? If mathematics is the art of explanation, what does math explain? Kirsty, did you get to think about that?
Well, I did, and I was thinking because tonight we're going to be talking about order, that when we think about explaining mathematics or using math to explain something, we usually have to be very ordered and clear and precise. And I know sometimes I think about when my kids were young, especially, and they were really excited, and you get like those popcorn explanations. You get a little bit here and a little bit there, and oh wait, but then I need to tell you this. And you're trying to put the story together, but math helps to train us maybe to be a little bit clearer in our explanation to people.
I think I like math because it explains why art is beautiful. It explains why poetry is inspiring. It explains why the sun gets up every day. I mean, there's so many different applications of mathematics that makes it so that it's interesting. So it'd be really nice to hear in the chat. I see Julie's already here helping us. If any of you have some ideas about just what does math do, what does math explain for you? But more importantly, how do you include your children in those ideas or conversations about it?
I'll share one quick story. So the kids, all grandchildren stories, but they were finding ladybugs. So we were counting the black dots, and Nora had 3 ladybugs. And so in nature, God created these beautiful bugs to have dots, to have some quantity of something on it. And so she had fun counting the dots and saying that they were twin sisters because they had the same amount of dots. And we had this whole conversation, but it's just God's character is in math. I think that, yeah.
Proudy, a good answer.
Anyone else? It's a quiet group.
Well, they're all just getting on.
I
That's why we
know.
talk for a few minutes to give them time to
Yes.
warm up, right?
Yes.
It's anyway, so we keep saying each week that map team has identified two main reasons why math is unfamiliar. The first one is because it's a universal language, but it's a foreign language. And today we're going to be looking at a lot of notation that hopefully will clear up some definitions that can be confusing to the general public. And then the other reason is because with the way books are edited and changed all the time, so publishers can make more money, the whole canon of math, the order of math, the way that you would go through math in a very systematic way has been lost in modern education. You know, I tell people a lot about how my grandmother, who only went through 8th grade, could have told you what Euclid's first 48 propositions were, because they were numbered, and everybody in the culture who had any academic background, that's what they studied in those middle school years. And so we're trying to recover through the math map that similar idea, and hopefully bring students beyond 8th grade geometry the whole way towards mathematical preparation for post-high school experiences. So you're welcome to join our discussion now. We're talking about math map lesson 8, equations. So feel free to turn on the chat at the bottom. We're going to talk about a lot of notations tonight that clarify order of operations in equations. But I'd like to thank our sponsor, CC Connected, where the math booklets discussed by the club tonight can be downloaded by Classical Conversations members. And you can look ahead to the book club schedule on leebortons.com under the Math Map Book Club tile. And I'm going to ask you to work through lesson 9, straight lines, 2D geometry. It's our first 2D dimensional unit for this series of discussions. So give that a look before you get on next week, and you go to ccconnected.com to download it. All right, and please just show up, even if you don't get to work through the booklet. So before we go ahead and have the general conversation, set us up some more, Kirsty, with tonight's conversation.
Sure. So we're, like you said, we're in our last week. And so we're going to start off with some thinking for everybody here. And so we're going to talk about order of operations. And we are using a different mnemonic. And we're going to talk in a minute, compare the mnemonics that you may be familiar with what we're using. But ours is groups, indices, multiplication and division, addition and subtraction, which we affectionately call GEMA. And so let's take a look at this, and I'm going to give everybody a minute to think through what would be the first step. And if you want to shout it out and say, this is what I would do first, you're welcome to, and then we'll reveal each step of this problem. What would be the first thing that you would do if you had to simplify this?
I would do what's inside the grouping, which is 3 plus 2.
All right. And what is 3 plus 2, Donna?
5.
Good job.
Yay, you got it right.
So we simplified our grouping symbols, and we replaced our 3 plus 2 with 5. So what's next? So I stands for indices. And so if you think back to last week when we talked about indices, that includes 3 possible things, right? We saw that in 3 different places. It was involved with exponents, roots, and logarithms. So what would be the next step for us to simplify?
The exponents.
The exponents. So, right. So we simplify those exponents, and 5 squared becomes 25, 4 cubed becomes 64. And now what's our next step? M stands for multiplication and division.
Multiplication, we just multiply our 4 times 25 so far.
So now we're left with 3 terms that are combined with addition and subtraction. Does it matter the order or the way that I put these together?
Left to right.
That's right. You go.
So we generally go left to right, right? We add or subtract left to right. But could I have changed it to 100 plus 64 minus 10? And if so, why?
Yes.
I
Because
hope
your
so.
answer is going, yeah, it's not. Yeah, I don't know
Subtraction
why.
is not
I can't
commutative, but addition is. So you could think of this as 100 plus -10 plus 64, and then you could put them in any order.
There you go. Right. So by
Right.
changing it around, so I just wanted to point that out, right? That we have our order that we're working through, but we still have all those other laws of mathematics that we can apply. So we could define this as plus -10, and then I can use my commutative and associative laws to move things around.
So before you finish it, let's talk about something homeschoolers. Car school is something we do a lot of. I know I'm in the car a lot when my children were little. So this was the kind of thing that you could do. So you could say to the kids, we're going to do countdown, start at 100. Somebody shouts out a number less than 100 and says add or subtract. And you just go back and forth in the car, adding and subtracting numbers till mom's in the parking lot and everybody's got to get out.
Does mom
Right, 'cause
have to know if they're right or not?
No, and you get lost too. But the thing is, where you want to practice this is you want to do what Kirsty's pointing out. You want to get used to saying, wait a minute, 64 minus 10 is 54 and 154 is 154. Like getting them used to seeing the numbers that pair up well. Is what that game's for.
Yeah, because I think that would be a lot easier to add 100 plus 54 than 90 plus 64. So that's one of the gifts we can give our children, right? Is helping them to make their life easier. And ta-da, we all got our answer.
I did not get that answer, so don't say we all.
Okay.
Okay, can you go back a minute before you talk about this? So can you explain on the left what we're seeing and how it applies to the equation on the right?
Sure. So our G right here, right, is telling us to really what it's telling me I did is to go from this step to this step. I simplified my groups first. And so when I look up here, I'm looking for any grouping symbols. And so in this case, I have parentheses that tell me 3 plus 2 is a group. And so I have to treat them as a group first. And if I can simplify it, then I need to simplify it. So
what are some other grouping symbols we could use? Do you know in the audience? I'm going to go excruciatingly slow, Kirsty, through this. I want to make sure brackets, right? What else?
A division bar, like a fraction bar.
Braces.
Braces. Oh. Good.
Radical can be, right? There's all kinds of things. Our sign, if I had the sign of 30 plus 40 in, right, I would want to do that first. So there's a lot of different ways we can group. So I simplified that. So now I don't have a group anymore, right? So even though we've got those parentheses still there, they're not really representing a group now, they're representing an operation. So now as we look at going from this step to the next step, our I tells us that next we would look for any indices. Now it's possible you have a problem that doesn't have indices or didn't have groups and you would just skip that step, but we wanted to make sure that we showed all the possible steps. So to go from here to here, I'm clearing any indices. So when I look at that, there we go. So when I look at this here, right, I have an index of 2 and that's an exponent. I have an index of 3 over here that's also an exponent. And so to simplify my indices, I'm actually going to go ahead and work through those exponents. So I have my 5 squared becomes 25. I have my 4 cubed becomes 64.
Okay, so 2 and 3 as your indices. What domain are the numbers 2 and 3 from? What's their narrowest domain?
Do you mean natural?
Yeah, they're natural numbers. Could they have been integers?
Yes.
Could they be fractions, quotients?
Yes.
Can they be quotients with a negative in front of them? Yeah. So
Yes.
one of the things we want to do too, and this is what N2K is so good at, is trying to show the students you can memorize quickly, not just these natural numbers, but all kinds of other domains in the integers and do quick calculations.
Okay.
Right.
Kirsty?
Yeah.
Hey, I just had a question. How would you explain to a student like the 3 + 2? Okay, we do the internal, but in the group. And then how would you explain to them that you don't take away the parenthesis and that the 4 is multiplied by the 5? Like there's an invisible like sign, like there's a multiplication going on there. How do you explain that to keep that in their heads so they could see, I'm going to simplify this, but I'm going to keep the parenthesis?
So I would come back up here and say, okay, well, and maybe that would have been a better first step, is to first, let's go back and say, what is it that we're doing? Let's read it first before we even start to simplify. And so if I go back and I read it, I say I have 4 times the quantity 3 + 2 squared minus 10 plus 4 cubed, right? And so once I read it, that's going to help me go, okay, I have 4 times whatever this is. And so now, yes, I'm simplifying it, but I still am doing 4 times that. And so it was a multiplication symbol before, but it also identified a group. So now that group's been simplified. So now it's just showing me I'm still multiplying. And if you have a student who really struggles with that idea, then you could always rewrite this and say, 4 times 3 + 2 squared, and then 4 times 5 squared, and have them write both symbols until they're comfortable with it.
Thank you. That's helpful.
It's good, Kirsty, because again, that's one of the things that the math map is trying to resolve, is just to be really precise in our notations and what they mean. And I think some people who are used to getting to a math book and just running through calculations might be a little bit frustrated with the curriculum, because we've embedded so much where they just have to read something or match it or identify it, really see the grammar that's in front of them and the notations.
I really love that you guys did that. I think it was just in the audio glossary that I learned how to say that times the quantity 3 + 2. That's so helpful, because I feel like as a homeschooler, I look at that stuff, but I don't really know how to say that sentence necessarily, right? So I love that you have it written out, like, this is how you would say that, approaching the limit, blah, blah, blah. That's stuff that I don't have in my grammar. And that's been super helpful to me.
Good. Good job, Kirsty.
Thank you. Well, that was Jill, actually one of the pilot tutors. You can thank her for the audio glossary, because she would say, how do I say this? And I said to her, well, make a list of the things that you want to know how to say. And that turned into that audio glossary. So I'm glad that you're finding that to be helpful.
For sure.
I would like to challenge somebody to be brave and read the bottom number, the one that's in the A row, the very last one.
154.
Is Gianna right? What is the common error we say and our children copy us in? What do they say?
154.
That's right. You don't say 100. What's the and mean when it's in a number?
Decimal point.
Yeah. So if it was 154.6, it would be 154 6/10. See, arithmetic, we make light of arithmetic and think it's not important, and then we wonder why they stumble in algebra.
All right, Lee, are you ready for the next slide?
Well, what else would you, on that, what I was talking about too is on the chart on the left where you have the step 1, 2, 3, 4.
Yeah.
Yeah, could you explain to us where that came from and how they
Sure.
would have found that if they don't know?
So, so this over here, right? So this is from our charts, which I know most of you have not seen yet. But week 8 has 4 pages of charts, and so this is one piece of that. And so it's telling us that first, when we're dealing with expressions, So we're not worrying about a comparison symbol, right? So we may be looking at 1/2 of an equation, right? Or there may be an implied equal because we're replacing it with something, but we're looking at something we're not trying to solve. We just have a group of terms, and we want to simplify them. We want to write that with fewer terms, with the simplest that we can. So it's hard to define simplify, right, without becoming circular, but that's what we're doing. We're looking for that compact or efficient form. And a lot of times we're going to take a lot of numbers and replace them with one number, or we may have variables. We may have some variables in there and we're combining like terms. And so we end up with a variable expression. But usually we're working, I like to think of it from the inside out. So if I have groups, I have to start at the inside and then I work my way out to simplify and combine like terms. And it's a process that sometimes, depending on if I have a lot of groups, I may have to go through this process multiple times, right? So if I had a more complicated, we didn't point that out, we just said we were simplifying the group, but within this group over here, right, we've got 3 + 2. I could have had 4 times 3 + 2, right? And then I would have gone through and I would have said, okay, within my group, do I have a group? Do I have any indices? Did I have any multiplication? I only had addition. So it was easy to just skip straight to that, right? And so there's this sense that I'm going to start inside and simplify and then move out. So I start with those groups. So here's some examples, right? I might have 4 + 3 that's being squared, or I might have sine where I'm looking at some angle sums. My indices, right? Here's some examples. I have my exponents, but I could also have my roots. Multiplying, when we're multiplying, we can also think of that as dividing. And we always move left to right, especially with multiplication and division. We're going to move left to right, doing both. So we don't separate them out. We do whichever ones we come to. So here we would have 6 divided by 2 + 4 minus 2 times 5, and that would simplify to 3, right? Plus 4 minus, and that should be 10. So there's a nice little error I just found right there. I'm going to make a little note in case I haven't already fixed it. And then
this is really why we're having these math discussions, so we can find our errors.
So there we go. We have 3x moving left to right, right? So now here I'm going to multiply across. I'm going to distribute my 2 across my x minus 1. So all I'm doing on that step is multiplying and dividing. And then finally, I would be adding and subtracting, again, left to right. And I say that, but here notice, even though I would be going left to right, I have to look for my like terms. So I'm going to have my 3x, look for my like term, which is -2x. Then my 5, look for my like term, which is 1. And that's where I get my x + 6. Okay, so that's our. All right.
So we're trying to just be really precise, and you finding that error made me think of one I found on something I made today. We have this problem in the naturals where there's a car going up a slope, and he's actually going up the slope in the wrong direction because he's going from right to left. And so we had to change the problem to make sure the car went from left to right, because we want to be so sure your children are doing everything left to right, whether it's reading a graph, looking at an image, or doing these equations, that they from the early on always have that habit.
I'm gonna,
Go ahead.
there we go. All right, so let's talk about, so we've just talked about what we call it, GEMA, but what do you remember? Right? Can anybody tell me, why does my dear Aunt Sally need to be excused, please?
Well, it's PEMDAS, right? Please excuse my dear Aunt Sally.
Yes.
That we memorized.
Right. So how does that compare? So look at the problem that's there, and how where do we take, what did we change? What would you put together between PEMDAS and GEMA?
Well, so the problem that we've always had is, like you say, parentheses, but parentheses really means in PEMDAS parentheses, brackets, braces, division bar, any symbol of inclusion at all. And that can be confusing. And in the G, you just have any group, right? So it kind of consolidates it into I'm thinking of logic, like you're going up a category, like the category that contains all of those things, rather than just the type parentheses.
Great. Kirsty, I think that's better than our explanation. That was good.
It was very good. Anybody else want to share something that they see comparing those two mnemonics?
But the exponents, that's not an exponent, the square root of 2, right? Am I right? So that's an index, as we learned last week.
Yes.
So your indices have, what did we learn last week? There was 3 of them. Roots.
Roots roots. I think of, okay, I should remember the word, an exponent, like raised to the power, and then a log.
Yeah. So she
Okay.
could have had a log problem here.
Yeah.
And Tanya said with PEMDAS, a lot of people will multiply before they divide and then add before they subtract, right? But we want to make sure people know, no, those things go together. So that was really early on. Lee really challenged me to look at our order of operations without using PEMDAS, because she's like, okay, we use it, but people don't always necessarily understand it. And so I actually spent some time and really dove deep into why the order of operations work. And I had this whole really long explanation, and Lee said, no, that we can't teach that to anybody. So we need something simpler. And so that's where we came up with GEMA. So I can tell you, because I did actually work through it, that the order of operations is not imposed by man. It is not something that somebody somewhere said, this is the order of operations. It is fundamental to the way that numbers and operations work, that it has to go in that order. And I discovered that for myself, which was really exciting. And so now I can report to you that this is a fundamental truth about mathematics. It is not something that teachers got together and said, this is the order of operations. It is actually fundamental to the way numbers work.
Would you call it axiomatic, Christy? Or Kirsty?
I would almost, it's almost deeper than
Yeah.
that. Like it's just this fundamentalness that we don't even have to agree on it, because it is, right? And it just is the way that they work. But then we come up with all of these shortcuts to help us remember. And one of the things that was interesting is, if you look globally, for example, in India, they use BODMAS, which is brackets, orders, then division and multiplication, addition and subtraction. So we decided we wanted to be something that was more global, both global numerically and operationally, but also global in terms of, we've got CC families around the world using this, and we wanted this to be something that was not necessarily American centered. And so that's why we came up with this. So here's a challenging problem. So let's look at this and see if we could simplify this at all. So does anybody see a first group that we might want to look at?
Maybe all of that's inside the radical.
So let's take a look at what's inside the radical first. And so we have a fraction, and I think it was Carrie that pointed out that fraction bar can be a grouping symbol, right? So we first want to look at our numerator and our denominator. Our denominator is just a number, so I can't do anything with that. But my numerator is a difference, so I could simplify that. And what would that simplify to?
9.
That would become 9. All right, so now, and then I think Donna was pointing out that that radical itself could be a grouping symbol. Can I simplify 9/4 any?
Oh, not
Yeah.
9/4 by itself. Go
Yeah.
with this. Go ahead.
Couldn't it be 3/2?
So once I look at my index, but looking just inside at 9/4, 9/4.
Oh, no, I cannot. No,
No.
not inside. Right. No.
Not inside. So now, so there's my group. So now let's look for our index. And so that's where you guys were going. So in this case, it is a radical. And so what would the square root of 9/4 be?
3/2.
3/2.
Do you still call that 2? Is that an index? Is that what you, I mean, I
Yes.
know that's the index. Okay.
So that would be last week. So if you're sitting here
Okay.
going, why is that an
I
index?
missed that.
Watch last week's. So yeah, so that too, and a lot of times we leave it off, right? So one of the things that we've talked about in the math map is all of the things that we just hide from students, the ones, the zeros, the 2s on the radical, right? If it's not there, we go, oh, well, it's just a square root. Instead of saying for kids to go, well, no, look, there's a 2. That means there's got to be 2 of whatever's inside until they're ready to leave that behind. So it's normally hidden. I wrote it here because I wanted us to be really clear that that was our index. All right. So next, any multiplication and division that we want to look at. I'm going to write the rest of this.
I was gonna say you could do the 6 times the 3/2, or you could make the 3/2 into 1.5 and then multiply it times 6.
So I will tell you that I always leave my fractions as improper fractions until I get to the end. And that way I always know that I'm not dealing with 1 times 1/2. It's always really clear to me that it's 3/2.
Kirsty, why? Is that from experience or is there a law you're basing it on?
No, it's just from experience. And because I can't, if I did 6 times 1.5, as my problems get bigger, I really have to know that this is 6 times 1 plus 6 times 1/2, right? I really have to be able to think through that that's a distributive problem. Whereas if it's just 3/2, I don't have to deal with that. They're just messy numbers to work with. So until I'm ready to, oops, I didn't mean to do that. Until I'm ready to work, like to get down to my final answer, I will always use everything. Oh dear, sorry.
It's time for our ad. Oh, go ahead.
All right, so this was 9. We got to 3/2. We agreed we're going to keep it as 3/2, and we're going to multiply it by 6. And so what would 3/2 times 6 be?
18/2.
18/2, which is,
Yeah, so would you reduce or model? Most mathematicians, I think, reduce before they multiply. Is that true?
yes, I think most, in this case with small numbers, I would say it's a 6 of 1, but I could have said that this is 1 and this is 3, right? I could have reduced there, and either way I would have gotten to 9. And so that would be my multiplication and division. And then I'm left with addition and subtraction. And the reason I wrote this the way that I did was just to point out that even though my subtraction is first, it's covered under that addition umbrella. And so I could do 9 minus 3 is 6 plus 8, and it gives me my 14. All right.
So what this problem shows to me, Kirsty, is that it's just so important for our kids to get down their math facts, because when there's harder numbers like, say, 3 and 17 and 51 or 26 and 52, that if they're not really good at those basic multiplication facts, they end up spending time multiplying things they could have reduced first.
Yes, that's absolutely true. All right.
Okay. All right. So thanks to our sponsor, Classical Conversations, ccconnected.com. where you can go to download the math map, Naturals Beta, where we're having that available for all the CC members so that before their children get access to the map curriculum, the parents can be doing just what we're doing here and work through the curriculum. It's the first grade curriculum. Shouldn't take you very long to go through it. And to refresh your memory for those of you that love math, and to help those of you that were maybe not so happy with math, to just see that it's accessible and to do a better job, because now that we're all grammarians as classicalists, we know how important it is to get the language and the math facts right before we do anything else. So thank you, Classical Conversations.
All right. So we've talked about GEMA and we talked about simplification. And for many people, PEMDAS is there and nobody considers how useful it could be for something else. And I actually remember helping somebody as an adult student in an algebra class. And I said, well, this is the reverse. And he said, nobody in all of his years of teaching had ever explained that to him. And so we're trying to be really clear with the math map that simplification, right? What we just did of combining like terms, it's a combining and putting together. And that's where we use that order of operations GEMA. When I want to solve, what I'm talking about now is an equation or an inequality, and I'm trying to find the value values that make it true. I'm trying to get down to really, I'm isolating now, I'm separating out that variable. And so this is really an algebraic skill. So all of our students, right, should be able to simplify. Solving becomes more of an algebraic skill because now I'm isolating that variable in order to figure out what values of that variable make the equation true. And so as we look at this, if simplification was combining and I used GEMA, now I want to separate, which is an undoing. And so I'm going to use the reverse process, right? And so if I knew GEMA, now I can use AMIG. And just like GEMA, right, I might sometimes have to go through it more than once. AMIG, I may have to go through it more than once. And so we've tried to come up with clear examples tonight to show you. These are actually examples from the curriculum itself to show you how this works. So let's go ahead and take a look at this first thing that we have, and let's start by reading it. And so it says 6 plus 2 times the quantity x plus 3 squared is greater than 12. Okay. And so my goal, right? My goal is to get this x separated by itself. So everything that I'm doing, it's like peeling back the layers of an onion so I can get down to x by itself. So if I was putting together, the last thing that I did was add and subtract, right? The first layer of the onion that I want to undo is any addition and subtraction. And so when I look, here's the term that has my x in it. So do I have a term that doesn't have an x in it that's being added to it?
Your 6.
My plus 6, right? It's got a hidden plus in the middle of it. So if I wanted to get rid of that 6 on the left-hand side, how would I get rid of it? I've added it.
Subtract it.
I'd subtract it. If I do that to my left side, what do I have to do to the right side?
Same thing.
Same thing, right? Because now we're talking about equations or inequalities. So I always do the same thing to both sides to keep that balance. And so what would 12 minus 6 be?
6.
Oh, hang on. I got to turn off the pen so I can click this. Oh, I clicked the wrong. Well, that's weird.
You're giving it all away.
I put it all the way.
It's okay.
All right. So we've got 12 minus 6. And that leaves me, right? So I added or subtracted, and I've got my 12 minus 6. So now the next thing I look at here is, here's my x plus 3. Right. And again, this is what I'm trying to isolate. So is there anything I need to multiply or divide to get that x plus 3 by itself?
2.
Divide by 2.
I'm going to divide by 2. And so that's where I see here, I had my 12 minus 6 gave me 6. I'm dividing both sides by 2. And I'm left with x plus 3 squared. So then my next step is to look and see if there's an index.
Mm.
And so is there an index on my left-hand side? Right, I was squaring it.
Yes, the 2.
The 2. So in order to undo a squaring, what would I do?
Square root.
Square root, right? And I'm just going to put here, there's my hidden 2. And so I take the square root of both sides and I'm left with x plus 3 on one side. And on the other side, notice we're saying it plus or minus the square root. Because we know that when I multiply 2 positives, I get a positive. If I multiply 2 negatives, I get a positive. So either of those answers would make this true. And then my last step.
Wait a minute, Kirsty, don't you want a 2 above the first 3 there? Would you keep writing your 2?
Where?
Like an I, column I, you wrote a 2 on the left, you should have had one on the right
On the
also.
right, yes.
Yeah, and then, okay.
I didn't choose, yes.
Good.
All right, and then, so my last step, so notice here, I'm down to my group, right? And so it says, okay, you're left with your group. You can't see that. I always forget. So you're left with your group here, right? This was my group. And so now I have to start that process over to solve within that group. And so I'm going to start over. And is there addition and subtraction? There is. I have to subtract that 3. And so my answer ends up being that x has to be greater than either positive the square root of 3 minus 3 or negative the square root of 3 over minus 3 to make this true.
So Kirsty,
was
I
the
should have
most-
kept a parentheses then on that G line so that the x plus 3 to the student would still look like that
Like
group.
the group.
I think I should do that.
So
What
can
do you
I,
guys think?
well, I was actually just thinking, I'm wondering if the equality or inequality isn't actually indicating 2 groups, a group on each side.
So what do you mean?
So, because we talk about terms, so, but the terms are with on each side of the, like right now, so we have an inequality, right? So you have x plus 3 on one side. So isn't that a group because it's on one side of the inequality?
Well, we're really only when we're solving, we're really just examining that left-hand side. Now on the right-hand side, I might end up with if I had not gone through and simplified each step on the right-hand side, I might have some things I need to simplify on the other side. But when I'm solving, I'm always just looking at that one side because it's all about separating out and isolating my variable.
That was
Well,
such
maybe
a
it's Carrie's
genius.
thing. But maybe
Yeah.
Carrie's thinking though, is if from the beginning given it had been 12 minus 2 squared, there would have been a group on the right and a group on the left. Is that what you're trying to say, Carrie?
No, I'm just wondering if when we're talking about groups in general, like because you'll simplify the left-hand side and you'll simplify the right-hand side. You want to make sure both sides are simplified. That from a student's perspective, does that equality or inequality indicate a group that can be simplified?
So remember right now we're solving, not simplifying necessarily. Had we, right, so without getting too deep in, right, there are times where I'm going to have to simplify before I can solve.
Right.
There may be I have to do GEMA to simplify. Now I'm doing AMIG to solve. And then I might be left with something at the end where I'm doing some simplification on the other side.
Gotcha. Okay.
Right. Does that help any?
Yeah,
So they're not,
it was
they're
just
not,
a wondering.
yeah, they're not really, I would not say that you've got 2 different groups going on because it's just where our focus is.
Okay.
Yeah.
So I have a question. It kind of goes back to what Lee was saying about the parentheses. Do you even need the parentheses under the radical in the I line.
Mhm.
Well, because it's the whole thing. Okay, so dropping the parentheses, I think, is because you just are left with the x plus 3. You don't necessarily need them at that point. So I think what Lee was asking is leaving them there. It's one of those, it's like you can leave them, but they do nothing for you with or without them at that point, because you solved for the group from the I to the G line.
Correct.
It just helps the kids to see it's still a group.
Or
But it doesn't matter. You've solved for that group.
Right, we just
You've
mean
now
for little
solved
kids
it.
looking at it,
Separates
it's
the
not
steps.
hidden for the kids.
Yeah,
it
it
can be-
separates the step, the index step and the group step. It separates it into two pieces, even though we would do it automatically at the same time.
Mhm.
I think that's what it is. It's just until students get familiar that sometimes you're going to help them see this was my group. I don't have to write it as a group anymore. I could just write X plus 3, right? Some students might need to see that extra step of I took my grouping symbols away because I don't need them anymore. But they may need to track it. So that is probably something that depends on the student, the level of detail that they're going to need to help them track that through. So, but remember, solving really is an algebraic skill. So that's going to be something that we're going to focus more with our challenge students than our younger than challenge students. Because we really are now getting into that algebra, right? So we've been simplifying, and if we know how to simplify really well, and then we help them to see that algebra is kind of an unsimplifying, because we have to get back to that variable, then it's going to help them to see how what they've been doing, right? All of this arithmetic is building up to figuring out these missing pieces.
I think what's funny is, you've used the word "un" a couple of different times. So for instance, in arithmetic, we teach the children to distribute through a problem, but mathematicians never use the word undistribute when they're trying to find the factors. And so I think it's really great to help the kids find kind of their own words and say out loud what they're doing, because then it helps them to own the equation. And that's one thing you can tell those kids, like when they're out there playing sports, a dad will yell out, you own that field or you own that basket, but we should be yelling, you own that math equation.
All right. I don't think we have
Great.
time to talk about this, but this is just the problem that we simplified. I just replaced one of the values with an X to show how we could have worked this backwards, but we're already over time. So I'm going to stop there and read that for God is not a God of confusion, but of peace. And a lot of versions say he's not a God of disorder. Right. And so when I talked about the fact that the order of operations was just fundamental to the nature of the numbers and the operations, right? We see that, right, God gave us that order. Man did not come up with that order, but it was fundamental to numbers that God gave it to us, right? That God was the author of that.
Good. Well, thanks again, Kirsty, and thanks to all of you. Remember, learning the language of math helps us to see the unseen. Take advantage of your CC membership and prepare yourself to redeem your love of math. See you next week.
Yeah.
All right. I hate being the one to hit end, but I'll be brave. Have a great night, everybody.